So now we are going to understand the solidification and cooling. Usually, most of the case, we understand the time, surface tension, gas solubility, porosity, how porous. Uh, okay, we already understood about this temperature graph when we melt the metal from initial to melting point, and then we keep giving the heat until it becomes a little bit hotter than the melting point pouring temperature. And then when we pour the molten metal into the sand mold or other molds, then it solidifies, and latent heat of fusion is released to change the phase from liquid to solid. And then we further cool it down a little bit higher than the atmospheric temperature. This is usually the atmospheric temperature, which is about, in our case, it's usually 20 Celsius or 25 Celsius. Some of the heat transfer uh, through conduction, convection, radiation. You remember we did the heat transfer review. Radiation, E sub B, like black body radiation, is sigma T4. And then 1D conduction heat transfer. The T stands for temperature, small t stands for time, alpha is thermal diffusivity. Thermal diffusivity is another technical term which tells thermal conductivity, that whether if alpha is very very small, it means insulating mold. So if you compare alpha of sand, because there are different materials. If you have, look, if you have sand versus steel, okay. Look, when you have a sand mold versus uh, iron die, okay. When you have iron die, this is a mold, and you put the metal through this part, and then it's very rough sketch. This is so this is parting line. This is. So look over here, this is the sand mold. So you will compare alpha thermal diffusivity of sand versus thermal diffusivity of steel mold. Then you will tell me, Professor, alpha sand is less than alpha steel. So it means is known as the insulating mold. So these are important check criteria before you start jumping the finding the some times to solidification. You will, because time for die casting is a different time. Time formula, mathematical formula for finding the time of the sand mold is different than the mathematical formula of the die cast. So you have to find out through alpha. Okay, and I'm gonna show you thermal diffusivity over here. Please write down this formula in your formula sheet. And the time constant is L square over alpha, where L is the characteristic length. We talked about in the first lecture about the characteristic length, which varies, like V or volume over surface area is for a plate, and we assume plate thickness as 2L, because half of the L is the characteristic length or the dimension. It varies. I gave you the homework problem which you understand. The length, characteristic length for sphere is r over 3, for cylinder r over 2, and similarly for a sheet metal it is uh, b over a. And then we all also learn about the BO number. You remember the BO number? It is H L over K. That how uniformly the temperature changes inside the metal casting versus inside the mold. So if it is less than 1, then we are happy that we can use this formula for the time. Okay. Again, this is coming. So assumptions. No temperature gradients. The Beer number. Yes. Please draw this diagram. This diagram is telling us that the temperature of the molten metal increases. So imagine you have a sand mold, okay? You have poured the metal at this location, which is x equals to 0. And then the whole, you see, inside temperature is changing. Where this dot is still liquid. You see my point? So this is like a dot. You see my point? And this is to the surface of the mold. So this is the surface of the mold, near the mold, at the entrance. Mold interface with the sand. I would say sand with, this is all sand. This is all, what is this? Sand. This is x equal to 0, where there is a surface. And there is air. Outside the sand is air. Air is at maybe 20 Celsius. Okay. Then the mold inside, near the surface of air is almost the surface temperature of air. You see, but when you go closer to the inside, you are going inside. As you touch this cavity, then it has a solid, metal is becoming solid, and some matter is still liquid. You see the you understood? Now can you tell me, if I change, this is a sand mold, can you tell me, if I put a dye, steel, and this is inside the cavity, okay, whatever, this is steel. Steel is contact with air, okay, it's inside. So steel in the boundary. So I would say at the boundary, I would say steel is, when you just pour the metal in, inject the metal inside the die, then you suddenly change the temperature. You don't go slowly. Here you go slowly. The temperature of the sand increases slowly towards the mold, towards the casting. But here in the die, it is initially at air temperature. But as soon as you pour the metal, it suddenly jumps to the pouring temperature. That's the only difference between the conducting mold, or the die mold, or metal mold, die casting versus sand casting. Yes. Yeah, it's more expensive. That's why we avoid it. 60% comes through the sand mold. It's gonna help you to understand this. Okay, the next I'm going towards the derivation of time to solidify the matter. That matters, because you know why does it matter? Because you need to arrange some risers, and there is a formula, some blind risers, some open riser, and some risers are, let me show you. Some risers are like a spherical shapes. Like over here, you put a riser in the form of a sphere. There is a reason. Volume divided by surface area will reduce the shrinkage time. If you have molten metal, let me ask you, let me ask you, if this solid solidifies faster, or if this solidifies faster, does it matter? If the riser solidifies faster than the casting, you will not be able to pour, remove the shrinkage loss. You have to reduce the time of solidification in riser. Otherwise, it will not compensate the shrinkage losses. If it is already solid, faster than the casting itself, then it will not be able to push the metal through the riser to cover the rings. You have to reach. So therefore, the spherical shapes or maybe different shapes, it has different time constant. You see my point? Time constant. So heat flux per surface area is equal to mold. So at this juncture, the heat flux Q over A is equal to heat flowing through the from this uh, mold to the sand. The heat flux is same. That's why I wrote down the mold and the casting. You understood this point? Mold, I would say this is my casting, this is my casting, and this is my mold. So at this boundary, heat is transferring from here to the mold. The same heat which leaves the casting is entering into the mold. Heat flux per unit area, surface area. And some of the important formulae, and it's going to help you to find out the time. So I'm going to show you the formula. Don't worry too much about these things. Yes, yeah, this one, effusivity. I'm going to equate. Look, I'm going to equate it. The left hand side. This is heat flux at the mold metal interface equals to this one. So let me show you over here. This derivation. I will tell you the final formula which you will need for your form equation and the heat flux for the insulating mold. So you see it's going to be derived very quickly now. S stands for V over A, characteristic heat transfer length. Yes, this is the formula. Please note down this formula in your formula sheet. Time required to solidify molten metal inside the sand mold. This is when you pour the, this is when you pour the uh, over here. Look, this is when you pour the metal at the melting point. But what if you increase? What if you increase? So what will happen here? This, if you increase the temperature beyond this point and then pour it, and then you see. So at this is my, we call it as C delta T. So let me write down. You have to rho add this. So rho C delta HF plus CP delta T. So let me show you the next slide here. Yes, of superheating. So when you see, I would say this is your final formula when you have pouring temperature higher than the melting point. This is the melting point, agreed? When you are pouring temperature higher than the, you have to add this Cp delta T term in this numerator. And if it is not, if it's the same, then this becomes delta T becomes 0 when it is poured at the melting temperature. But usually we have to increase the temperature. So the next, I'm going to show you how to apply this formula into the numerical problem. So collect the information.